September I will be starting second year chemistry at Southampton. I've been working at uni over the summer and I've decided to take the opportunity to make a few videos just to go along with what you'll be learning in your lectures. The videos will help to explain some of the main concepts covered in inorganic, physical and organic first year chemistry. I'll discuss the basics and then go on to work through some examples so you can see how to apply what you're learning, which to me is the most important part. A bit like what you'll be doing in workshops, so hopefully really useful. The first one's on quantum numbers, so let's see how it goes. So quantum numbers generally, they give us information about the location of an electron. It's more of a general idea of where the electron is most likely to be rather than a specific location. There are 4 quantum numbers in total, so we'll start with the first one. The principal quantum number is given the symbol N. In general terms, this tells us which shell the electron is located in. So if we have an electron in the first shell in the 1s orbital, the value of N would be 1. In the same way, if we had an electron in the 2s orbital, the value of N would be 2, and it's in the second shell of electrons. That's just the first 2 shells that I've mentioned, but N can actually take any integer value from 1 to infinity. You'll probably only come across N values between 1 and 7, as these are the most common in chemistry. The principal quantum number tells us the most likely distance to find an electron. So, as we had an electron with n equals 1 before, this tells us it's in the first shell, but that also means there's a better chance of finding it close to the nucleus than if we had an electron with an n value of 3. From this, we can also find information about the energy of the electron. As the electrons closer to the nucleus will be more strongly attracted to the positive charge of the nucleus, so will be more stable, as there is a larger force of interaction between that electron and the nucleus. As they are more stable, they will also be at a lower energy, as it would take a lot of energy to remove them. The second quantum number, called the secondary quantum number surprisingly, or the orbital angular momentum quantum number, is symbolised by the letter L. This generally tells us which subshell the electron is in and the shape of the orbital. L can take any integer value from 0 to n-1. The most common values you'll come across are these ones. And that is because they symbolise the s, p, d and f orbitals. But L can also take values higher than 3, so just bear that in mind. If we had defined n as a value of 2, then L can take any integer value from 0 up to n-1, which is equal to 1. So we would have L equals 0 and L equals 1, both possible values of L when n equals 2. From this, we can tell it is possible to have both an s orbital and a p orbital when n is equal to 2. The third quantum number is the magnetic quantum number and is given the symbol ml. On a very basic level, if we write down all the possible values of ml, which we can find from a specific value of L, it will indicate how many orbitals there are of that type. It also tells us about the orientation of the individual orbitals, so we can see where they are positioned in space in relation to the other orbitals. We can find the possible values of ml as the allowed values are integer values between and also including -L to +L. So if we have L equals 1, which as we know would represent a p orbital, the values of ml would be -L, which equals -1, and then we'd add 1 to our first ml value to get the next highest integer value, so we'd also have an ml value of 0. and we need to make sure that we stop when we get to our plus L value, as the range is from minus L to plus L. So if we just note that our highest ML value is plus L, so equal to plus 1, then we know when to stop finding the next highest integer. So the next one is actually plus 1, as we're adding 1 to our last ML value of 0, and plus 1 is our limit. So we have ML values equal to minus 1, 0 and plus 1, 3 ML values in total. As we know from before, an L value of 1 represents a p orbital, and we have 3 possible ML values when L equals 1. We can see that there are 3 p orbitals in this shell of electrons. One would have an ML value of minus 1, one would have an ML value of 0, and one would have an ML value of plus 1, and each of those would have a different orientation. You may have noticed that we didn't need to use a value of n to work this out, so we can generalise this and say whatever the value of n, there will always be 3 p orbitals in one shell. So in other words, we can say we have 3 np orbitals, and you can just insert the value of n. All 3 quantum numbers so far can define an atomic orbital. So the orbital defined with the quantum numbers n equals 1, L equals 0, and ML equals 0 would be in the first shell as n equals 1, would be an s orbital as L equals 0, and would be the only orbital of that type as we have only one single value of ML, which is also 0. If we look at an orbital represented by the quantum numbers n equals 2, L equals 1, ML equals minus 1, 0 and plus 1, we can see that n equals 2 represents the second shell, L equals 1 represents a p orbital, and the 3 ML values show there are 3 orbitals of that type. So this set of quantum numbers represents the 3 2p orbitals. In a hydrogenic atom containing only one electron, these 3 2p orbitals would be degenerate, so they would all be energetically equivalent. For atoms with more than one electron, this isn't the case, but in both cases, they would be represented with the same quantum numbers.